We begin our exploration of complex numbers with this web sketch, in which students are introduced to the rectangular and polar forms of complex numbers, as well as several different ways they can add complex numbers together. So here we have two tools at our disposal: a vector tool, which creates complex numbers, because we're thinking of complex numbers like vectors, and a tool to measure a complex number in its rectangular form. So let's start by constructing a complex number. I'll tap on the vector tool, and I see a preview of my vector and this point z that's glowing, and this glowing indicates that I need to place the point. So I can tap anywhere I like to place it. So here I have my complex number z, and I can drag it anywhere I like. And now, if I'd like to see it in its rectangular form, I'll tap this tool. And notice I have a point here that's glowing, and I'm going to tap on point z to attach these 2 points. And there, the tool is complete. So now I have the rectangular form of z. I have its real and imaginary components, as well as the rectangular form written out in whole. And as I drag z, I can see those values change. I can drag z onto the real axis, and notice when I do, the real axis lights up and point z glows. If I let go while z is glowing, z is now attached to the real axis, and I can see the effect that that has on the rectangular form. If I want to remove z from the real axis, I'll just tap the undo arrow. I can also explore what happens when I attach z to the imaginary axis and then drag it. Now I'll move on to page 2, using the page controls in the lower right-hand corner. And here again, I have the tool, the vector tool, for creating a complex number. But now I'm going to look at the polar form of that number. So again, I'll tap the tool, and I have my glowing point z, and I'll attach that to the head of my vector. So now I see some data about z in polar form. I see its length, as well as its argument, the angle it makes with the positive real axis. And I can drag z all around my complex plane and see the effect that that has on those 2 values. And as before, I can attach it to either the real or the imaginary axis to explore those special cases. Moving on to page 3, we're going to construct 2 complex numbers and then add them together. So I'll use my vector tool twice. Right now, both of these complex numbers are labeled z, but I want to change one of those, so I'll tap the label widget. And now I'll tap this point, and I can change the label to w. So here I have z and w. I'm going to measure each of these in its rectangular form. And now I would like to construct z plus w. So given this information here with the real and imaginary parts, I can add together x sub z and x sub w and y sub z and y sub w, and then use that to plot the sum. And to do that, I'll use the calculator. So I'll tap the calculate tool. I'll tap in this glowing rectangle to reveal the calculator. And you might, if this was a normal calculator, just actually enter the value 0.59 and add it to 1.48. But Web Sketchpad's calculator is special. It allows us to do something more powerful. Rather than enter 0.59, I'll simply tap on x sub z, and then I'll add to that x sub w. and tap OK. And what's nice about this is that when I drag either W or Z, we see that this sum is updated as I drag. It's not a static value. Well, I can do the same now for my imaginary components. So I'll add x sub z plus, y sub z plus y sub w. And now I have the real and imaginary parts of the sum, z plus w. And I can plot those using the plot as x plus yi tool. So I'll tap on that. And I see a preview of an x and a y value. The x value is glowing, and I am going to match that to the x value that I would like to plot, the real value of my sum. And that's this, x sub z plus x sub w. So I'll tap that to merge those together. And now the y value is glowing. I need to match that to something. So I'll match that to y sub z plus y sub w, the imaginary part of the sum. And here I have it. And if I move w a little bit, you'll see that that point here is plotted. And that is the sum of the x's and the sum of the y's. So here we have the sum. And I can represent that as this vector. I'll match that to this point. And I will label that point by tapping on it as z plus w. So this is the numerical approach to finding the sum. If I move on to the next page, now we no longer have those tools, we just have a translate tool. So again, I'll construct two vectors, two complex numbers, and let's label one of these as w. And now we're going to take advantage of the fact that if we think of complex numbers like vectors, we can add them just like we would vectors. We can start with vector w and add to that vector z by placing the tail of vector z on the head of vector w. So I'll tap on the translate tool, and we see a preview of a point that is going to be translated by some vector. So what is the point we'd like to translate? Well, I'm going to translate starting here at the head of w. And what is the vector we're going to translate this by? Well, it's vector z. So I'm going to tap to merge this glowing point to the tail of vector z, and then tap to merge this glowing point to the head. And, excuse me, here we have the sum, as before. On this next page, we have, instead of a translate tool, we have a parallel tool, and we can use that to find the sum. And in this case, we are going to take advantage of the fact that if we look here at z, w, and their sum, that these form a parallelogram. So if I tap on the parallel tool, I'm going to create a parallel line through the head of z that's parallel to w. So I'll tap to match this to w, and I'll tap to match this glowing point to z. And I'll create one more pair of parallel lines, this time parallel to z through w. And here is their sum. Z plus w. Now for future sketches, we don't really want to go through this effort of constructing the sum as we've done on these 3 pages. That took some work. It was good to practice this and see the different ways to find the sum, but we'd like a quicker way so that we can move on to other topics when we need to find the sum as part of those topics. So here, again, I'll start by building z and w. And to find their sum, we have a translate tool. And we are calling it translate because you can think of what we did here as translation to find the sum. And throughout our exploration of complex numbers, we're going to be looking at the arithmetic of complex numbers in terms of geometric transformations. So we'll start with translation as a way of representing the sum of complex numbers. So if I click on the translate tool, I see two complex numbers and their sum, and one of them is glowing. I'll match that to W. Now the other is glowing. I'll match that to Z. And here, voila, we have their sum of Z and W, which was a lot easier to do than any of our prior constructions. So we'll use this translate tool moving forward. We now move on to a web sketch that explores what happens when we dilate complex numbers. So here I begin again with my vector tool to create a complex number. I'll tap it, and on this first page we're going to look at what happens when the number is real, has no imaginary component. So I'll tap to merge it to the real axis, and as I did before, I can measure it in rectangular form, and I see that the coefficient of I, as expected, is 0 and remains 0. So what happens when we dilate a number on the real axis by a scale factor? So I will tap on my dilate tool, and I see here a point that's glowing. That's the number I'm going to dilate, and that's Z, so I'll tap Z to merge these together. S is my scale factor, so I'll just tap to place that in my sketch. And I can now look at the rectangular form of my dilation, Z prime. And it appears in this instance, and when I drag Z, that the effect of scaling by a factor of 2 is to take my real component, 1.17, and double it. And I can also try other values here, like 3, or as suggested here, values like -2 or 0.5. On page 2, we look what happens when we dilate a number on the imaginary axis. So just as before, but now we're merging Z to the imaginary axis. On page 3, we look at what happens when we dilate an arbitrary complex number. So here I'll tap anywhere in the complex plane. I'll look at the rectangular form of Z, and I'll dilate it. And I'll look at the rectangular form of my dilation, and I'll see how these two values compare when I drag Z. So lots of data that students can collect and analyze. On page 4, we switch to the polar form and look what happens to an arbitrary complex number when we scale it in terms of its polar form. So here's my vector. I'll dilate it. And then I'll look at the polar form of Z and the polar form of Z prime. And I can see what about those two sets of values I get is similar and what's different. And then drag Z to collect more data. Here on this next page, I'm going to construct a complex number z, and then I'm asked to construct negative z. And students can do this by using the dilate tool, dilating z, and changing its scale factor to -1. Here, students construct two complex numbers, z and w, and then are asked to construct z minus w. This is a nice challenge for them. They often don't know what to do with the minus w part. Here, the last page of our sketch, and building up from what we've done so far, students construct two complex numbers, z and w, and then are asked to construct 3z minus 2w. So we could start by dilating z by a scale factor s of 3. And as we go, it's very helpful to be labeling what we obtain. So here, this z prime represents 3z. Now we'll construct our next piece here, the minus 2w. So we'll dilate w by a scale factor of -2. And let's label that. So here we have -2w. And now we can add these together, 3z and minus 2w, using the translate tool. So I'll match this glowing point to 3z, match this glowing point to minus 2w, and here we have the sum. 3z minus 2w. A nice visual geometric way to add and subtract and scale complex numbers. Moving on now to our next web sketch, we're going to look at the effects of rotating a complex number and seeing how that affects, in particular, its rectangular form. So let's start with a complex number z. And I'm going to create a slider. And this slider creates a point on a circle. And as I drag it, it changes the value of radians. And I am going to use this slider to explore the effects of rotating z by different angles. This makes it easy because I can just drag point theta and change the angle by which I'm rotating z. So now I'm going to actually rotate z. I'll tap the rotate tool and I'll match z to the head of my vector. And now I see that theta is glowing, this amount that I'm going to rotate z by. And I'm going to match that to the theta that's already in my sketch. So I'll tap that. So now when I drag this point theta, it changes the rotation of z. So in particular, let's look at what happens when I rotate z by pi/2 radians. Well, it looks like here, probably should actually use the rectangular form tool to get some data. I'll tap to merge that to z. And here I have the rectangular form of z. And let's find the rectangular form of z prime, the effect of rotating z by 90 degrees, or pi over 2 radians. And we get some interesting data here about what happened. If I drag z, students can collect lots of data, and they can conjecture that the result of multiplying a complex number z, or of rotating it, I should say, by pi over 2 radians, is to multiply that complex number by I. So multiplication by I is equivalent to rotating by 90 degrees, or pi over 2 radians. They can also explore the effects of rotating by pi, or 3 pi over 2 radians, just by dragging this slider. Now, to begin pulling everything together, we'll take what we've learned and use it to multiply some complex numbers. We'll start by constructing 2zi when we're given z. Well, I know if I use my dilate tool to dilate z by a scale factor s of 2, that will give me 2z. Now, to multiply 2z by I, I'll apply the rotate tool. I'll tap on 2z, and I have my angle of rotation as pi over 2 radians. So here we have 2zi. And I can drag z to see the effect that has on 2zi. Now we'd like to construct z times 1 plus I. And I'm going to think about that by using the distributive property and writing this as z plus zi. So we already have z, and we'd like to add to z, zi. Well, we know how to construct zi. We'll rotate z by 90 degrees, and let's label that as zi. And we now, to find z times 1 plus I, we're going to take z and add to that zi. So we'll use our translate tool, and I will attach these 2 points to z and zi. And here we have what we're looking for, which is z times 1 plus I, which I can write as z plus zi. Now notice in our sketch we also have a right triangle tool. And I'm going to add some right triangles to my sketch, first using 1 plus I as the hypotenuse of a right triangle. I'll tap to merge that to 1 plus I, and I'll tap to merge this point to the real axis. And now I'm going to create another right triangle right here by tapping. And if you look at the blog post that accompanies this video, you'll see that in this post we begin to look at the lengths of the sides of our right triangles, the length of the hypotenuse, and we see that these 2 right triangles are both isosceles right triangles and similar. And this is the beginning of motivating in a geometric way the idea that to find the product of 2 complex numbers, you multiply their lengths and you add their arguments. And this approach, I am indebted to Al Coco in the book that he published, Mathematical Connections, A Companion for Teachers, which is the first place that I'm aware that this geometric way of understanding complex number multiplication is first discussed. So let's look at one more example of multiplication. We'd like to construct ZW. So here's Z and here's W. And we have W written in its rectangular form. And we're going to keep Z as just Z. And to multiply Z times W, we'll start again, thinking of this using the distributive property of scaling Z by 1.5. So we'll use the dilate tool, and we'll use a scale factor S of 1.5. And as always, we'll label as we go. So here we have 1.5Z. Next we have Z times 0.7i. So the first part of that is Z times 0.7. Again, we'll dilate. Z 0.7. So this point here is 0.7Z. And it's Z times 0.7 times I. So for that multiplication by I, we're going to rotate this point by pi over 2 radians. So here we have 0.7i. And we're almost done. Z times W is the sum of 1.5Z plus 0.7Zi. So for that, we'll use the translate tool. And here, voila, we have the result all done geometrically. So we have 1.5Z plus 0.7Zi. And as before, if you look in the blog post itself, you'll see this picture along with a discussion about why these two right triangles are similar and why the product of ZW can be found by multiplying their lengths and adding their arguments. Now, to bring everything together, we're going to construct a complex number Z, then we'll construct Z squared and Z cubed, and we'll use this construction to look for locations of Z for which Z cubed equals 1. Here's Z. I'll find the polar form of Z, and we see that it has a length, r, and an argument, theta, the angle it makes with the real axis. And we can use what we've learned about multiplication to find Z times Z, or Z squared. That product will be the product of the lengths, r times r, or r squared, and the sum of the arguments, theta plus theta, or 2 theta. So let's calculate that. We start with r squared, and we calculate 2 theta. We now plot these two as r theta. This is my r, my length of my complex number, and that's the argument. And here it is. Let's add a vector to that, and let's label it. So that is Z squared. All right, now we're going to find Z cubed. And to do that, we'll do exactly what we did before. This time we'll compute r cubed, and we'll calculate 3 times theta. And we'll plot those. And here it is. C cubed. Now I'm going to measure the rectangular form of z and the rectangular form of z cubed. So I'm looking for locations of z for which z cubed is 1. Well, one of those is right around here when z is 1. Notice I can't get it quite exact, but pretty close. And there are actually, surprise, other locations for which this works. So I can drag z and look at z cubed. And when I get around there, pretty good. I could wiggle this around a bit to try to improve it. Here's another location of z for which z cubed is 1, or nearly so. And I can drag z and look for another such location. And I might want to take this value of z, enter it into Google, for example, and have Google do all of the algebraic calculation of raising this to the 3rd power to see if indeed this geometric model is giving us the right information. I find it very nice to see that the two coincide. So now we're going to move on to a second model. Same task, starting with z, constructing z squared and z cubed. We have the r and theta values, but we don't have a calculate tool. So we can't construct r squared and 2 theta simply by using the calculator. So instead, we're going to have to go back to what we know about this geometrically. So to compute r squared, or to construct r squared in this case, since z has a length of r, to construct r squared, we're going to scale this by a factor of r. So this is the length we want of z squared, but we don't have the right angle yet. For that, we're going to need to rotate this by an angle of theta so that we construct z squared, which gives us an argument of 2 theta. So to do that, I'll tap on rotate. This is what we want to rotate, and we want to rotate it by this angle of theta sub z, so I'll tap that to merge it together. And here we have z squared. So I like being able to do this in 2 different ways. On this page, using the geometry of complex numbers, and on the first page, using the geometry, but using the calculate tool to perform it. And of course, you could continue in this manner to find z cubed. Let's just change that label here. That really should be z squared, not z prime squared. Perfect. So that concludes the end of this long exploration. I hope you found it interesting. And again, my thanks especially to Al Coco for putting this together in such a compelling way that lent itself so nicely to Web Sketchpad.